In this lesson, we're going to talk about natural base functions, which are all based on a number discovered by Leonhard Euler, a mathematician in the 1700s, that all stems from the following relationship. There's this number where if you take 1 plus 1 over n to the power n, and you plug in large enough n values, so as n goes to infinity, this number converges or gets really close to one specific number, and it's about 2.718. And I know a lot of these digits: 281828, and 4 or 5. I might as well show you the trick: 459045. I actually know this number out that many decimal places because I always remember. Most people use just 2.7 for this number, but I remember the year 1828, and then a 4590, 45 triangle, and you can impress your mathematician friends with the fact that you know this special number, which is E. This is the natural base, E, and just like the letters I and pi, those symbols represent actual numbers. In this case, it's the same thing. So E, for us guys, E we're going to let be approximately 2.7, and most people know E is about 2.7. Although, of course, it's an irrational number. This decimal place keeps on going on and on forever. There's, those digits never stop, and that's just as far as I know. Now, this natural base E can be used to create functions, and you should be able to tell just by looking at a function. Let's say I have f of x. If it's exponential growth, it's going to be a times e to the power rx. And for it to be growth, just like before, remember that a value has to be bigger than 0 first of all. And for this to be growth, your r value has to be positive or bigger than 0. And then you're going to have an exponential growth function. However, if f of x is a times e to the rx, if it's decay, we got to have the a value once again bigger than 0, but now r has to be less than 0. If r is less than 0, this thing will be a decay function. So one of the first questions I could ask you would be in the following examples. In this example, we're going to determine whether the function is exponential growth, decay, or neither. So kind of like in the last section in 8.2, I like to write down the a value, and in this case it's a half, which is bigger than 0, which is a half, and that's bigger than 0. So far it's not going to be neither. If your a value is positive, it's either going to be growth or decay. What we need to look at for these natural base functions is the exponent, and that the number in front of x. That's like your r value. In this case, the r value is 3, which is positive. It's bigger than 0. So because the r value is positive and the a value is positive, this is going to be exponential growth. If you take a look at b, in this case the a value is 2, which is bigger than 0, so it could be growth or decay, and r, the number in front of x in the exponent, is negative. It's negative 0.4, which is less than 0. That would indicate that this is going to be an exponential decay model. For c, my a value is negative 1. Right there, I could stop, because as soon as your a value is less than 0, it's neither growth or decay. So I'm just going to say neither. Another example that I can show you with e is simplifying with the base e. Guys, treat e just like you would any variable when you simplify. So for a, if I have 24e to the 8th over 8e to the 6th, I would say, alright, well 24 and 8, they're divisible. I can have that be 3. And then remember what you do with exponents when you divide like bases. You end up subtracting them, right? So it's going to be e to the 8 minus 6 power. So I'd have 3e to the 2nd power. And I would just leave it like that. That's the exact value. Let's look at this guy. I have 2e to negative 5x raised to the negative 2. There's a couple ways of doing this. One way is to distribute that exponent to both factors in the product. So I'd have 2 raised to the negative 2, and then e raised to the, now I have to multiply these two, right? And negative 2 times negative 5x would be a positive 10x. So I really have e to the 10x that stays in the numerator, and I'm going to bring this guy downstairs, making it 2 squared, and I can rewrite that as e to the 10x, and 2 squared is just 4. So I would simplify that expression to be the following if I don't have negative exponents. Something else you should be able to do is evaluate the natural base expression. What I mean by that is we need to actually use our calculators now to figure out, okay, what does this equal, or at least approximately, using our calculator. So what I'm going to do is the following. I'm going to bring up my calculator, and I'm just going to type in exactly what we see. So I'm going to put 3 halves, 3 divided by 2, and then it's times, and now there is an E button on your calculator, and it's, you have to hit the second and division button, and that brings up E, and then you can use the caret sign to raise it to any exponent you want, and if you hit enter, you'll get your approximate value. There is another place to get E, and I'll do this problem over again. If I do 3 halves and then do times second, and then if you hit this ln button, which you don't know what that ln means, and you will this chapter, when you hit second ln, it brings up E and automatically gives you a place to write the exponent. So you can just type in 3. So that button, I like hitting second ln when I know I have to raise E to a power. And you get the same exact value. So let's go to just 2 decimal places. We're going to have about 30.13, right, if we actually wrote that. So this is about 30.13 if we evaluated that guy. Now let's do the next problem. If I have to do e to the negative 0.021 power, I would hit second ln, just because that brings up that exponent for me. I can do negative 0.021, close parentheses, and I get about 0.98 if we round to 2 decimal places. So I would say that this is approximately 0.98 there. Okay, so using your calculator is kind of easy as long as you know where to find the button. Okay, let's go on to the next slide. And if